Let's jump into 11.7, volume of pyramids and cones. I'm glad that you're with me, and I hope this is helpful to you. Our essential question is, how do I find volumes of pyramids and cones? So make sure that you have your formula sheet here. Let's take a look at this. So we've just done, in 11.6, we did prisms and cylinders. And remember, both of those solids have two bases to them, whereas now we are doing pyramids and cones that only have one base. When they have two bases, all you have to do is take the area of the base. Remember, when we see the capital B, we say that as the area of the base. All you have to do is multiply the area of the base times the height to find the area of a prism or of a cylinder. When we're coming to pyramid and cone, since there's only one base for each of those, what we do is still the area of the base times the height, but it's only 1/3. It's only 1/3 of that. Remember how I showed you in class that if I was to fill up one of these cones, say the cone had the same height as the cylinder, there would be 3 cones of water necessary in order to be able to fill one cylinder, if the cone and the cylinder had the same area of the base and had the same height. So let's jump into it. You have here in your book an explanation of what I just kind of said there, and then these two theorems. I've put these in your notes for you. So this is a prism, and we know that because this apex, maybe even go ahead and label this again as an apex up here and also an apex here on a cone. You'll remember that in order for it to be a pyramid, all the shapes, all the polygons surrounding the apex have to be triangles, and therefore we use the equation for volume as 1/3 the area of the base times the height. 1/3 area of the base times the height. And what is the shape of this base? In this case it is a rectangle, and so if we were to call this base, so again, when I'm saying base, I mean lowercase base. When it's a capital B, we pronounce that as the area of the base. So base times width is lowercase b times lowercase w, and so we'll replace that for the area of the base, and then multiply it times the height, and multiply it times 1/3, and that'll give us the area of this pyramid. The area of the cone is very similar. We start out with the same equation. Volume equals 1/3 area of the base times the height. But in this case, the area of the base, or the shape of the base, is a circle. So therefore, the area of the base is pi r squared. So we plug in pi r squared for the area of the base, and our volume for a cone is 1/3 pi r squared. If you would put parentheses around that to remind yourself that is the area of the base, times the height of your cone. So let's do some examples. This is really simple now that we've already done the hard work in 11.6 of understanding how to do the area of a prism. It's the same idea here for the area of a pyramid. In this case, it is a triangular prism, so the area of the base is a triangle. So we go back to our formula sheet, and the area of a triangle is 1/2 base times height. So the area of the base, capital B, is 1/2 base times height. In this case, it happens to be a right triangle, so this can be our base and this can be our height. So our base is 4, our height is 6, 1/2 times that, and then times the height. And notice again that this is the height of the solid. So I'll put of solid, as opposed to this 6 is the height of the triangle. So be careful that you understand what height you are talking about. And multiply all that stuff together and you get 36. Here is a funky looking cone. It's kind of squished off to the side. But remember, just like we saw in 11.6 with our Cavalieri's principle, it's okay to squish it over to the side as long as, well, what we said in Cavalieri's principle was that as long as it has the same cross-sectional area, then it'll have, and also the same height, then it'll have the same volume. That same principle applies to a cone, and so what you'd say is if it has the same cross-sectional area for the particular height that you're measuring it at, since obviously the cross-sectional area changes as you get higher, then it's going to have the same volume, or yeah, same volume. So for our purposes, whether it is a right cone or a slanted cone, it's still the same formula. Volume equals 1/3 area of the base times the height. What is the shape of the base? The base is a circle, and therefore the area of the base is going to be pi r squared. So just plug in my 2.2 radius in here for radius, and then my height is the entire height of your cone. So whether the cone would be a right cone or slanted over even more so over here, it's still going to have the same volume. So our exact number is 7.26 pi centimeters cubed. They should go ahead and put the units there. Oops, cubed. Because you could say it that way, and that's the exact number. It's 7.26 pi cubed centimeters, or centimeters cubed. Or you could figure it out as a decimal and round it to the nearest hundredth, and then you'd have to put approximately. Since you rounded it, it's not an exact number. The pyramid, well, I think this is the, it's not the Great Pyramid, but it's however you pronounce this dude's name. Khafre's pyramid in Egypt. And do you guys know pyramids? All it is a huge tombstone. Weren't these guys prideful? Not that I'm not prideful. I am prideful, but these guys really thought well of themselves and thought that was a way to get them into the next world, was to make this huge tombstone and put themselves, their dead body underneath it. Interesting. But they have calculated somehow, or they're telling us, that the height of this particular pyramid is 144 meters, and the volume, what is that, 2,226,450 cubic meters. So if I had that information, knowing our formula, volume equals 1/3 area of the base times the height, I could calculate what the length of the side would originally have been. Because you see all the erosion, I guess that's what they're trying to do. But how would they know the volume if they didn't know? Yeah, they'd need to know what the length of a side would be in order to calculate the volume. So anyway, they are asking us to calculate the length of a side. And the shape of the side, we assume, this is a square pyramid. So it's base times width. In this case, because it's a square pyramid, it's a x times x. So here's our formula, or here's our equation that we plug in what we know of the volume, we plug in the height that we know, we want to solve for the side. So first thing we do here is multiply, to clear this denominator of 3, multiply both sides by 3. That'll clear this guy. 3 times this big fat number on the left gives me a fatter, bigger number. And then divide both sides by 144 and gives us this. I guess it's approximately because it comes up as a decimal. And then to get rid of the square here, you take the square root of both sides. And the square root of that number is approximately 215. So what they're saying is that if they start with a volume, we can find one of the other parts if necessary. And you guys can do that. The guided practice, this was, I thought, a little bit difficult. We will be doing this in class, these kinds of things in class, where we have to find the area of a regular polygon. That takes a good amount of work just itself. But let's just practice this volume skill. So I gave you a different problem here, gave you a square pyramid. And so use your same formula of volume equals 1/3 area of the base times the height. What is the shape of the base? The base is a square. What's the equation for the area of a square? It's a base times width. And in this case, your base is 5 and your width is also 5. Then you multiply that times your perpendicular height. I'm saying perpendicular because it needs to be this height that's perpendicular from the base. In the future, when we do, just in the near future, when we do the surface area, we're going to want slant height. But in this case, they're only giving us, and that's what we want, is the perpendicular height. So plug that in. Right cone, that should be no problem for you also. So go ahead and pause the video and do questions 1 and 2. Now let's look at example number 3. And here, these problems are so easy that not only are they trying to get you to review, and we will do that, review how to do the area of a regular polygon, but they also want us to include some trigonometry. So they do not tell us what the radius of this circle, the area or the base, which is the shape of a circle. We don't know what that radius is, but we do know that this angle here, going from the radius up to this slant height here, this side, is 65 degrees. And we do know the height of the cone is 16 feet. So in order to figure out the radius, just look at this right triangle here, and in reference to this angle, this is the opposite side, so we have the opposite, and we want the adjacent, we want the radius. So what trigonomic function uses opposite and adjacent? And it's tangent. So if we take the tangent of 65, that is equal to opposite over adjacent. In this case, our opposite side is 16, and we want to find what the radius is. So here's our equation to be able to solve for the radius. To solve for radius, we would multiply both sides by r. That would cancel out the r's on the right hand side, and then we would divide both sides by the tangent of 65. So my radius is going to be 16 divided by the tangent of 65, which I guess is approximately, if you round that to the nearest hundredth, 7.46. Yeah, okay, I'm sorry. Here's this kind of an enlargement of this triangle here that they have down here, a little bit easier to see there. And then we plug it into our formula. As you know, since this is a cone, the volume is 1/3 the area of the base times height. And what is the shape of the base? It is a circle. What is the area of a circle? It is pi r squared. And then plug in our radius that we know. And they should not plug in this 7.46. They should plug in this exact number here, so that you're not using a rounded number. When you do, you get an even more deformed number, so be careful with that. And if you plug all that in, then you get this approximately this number here. And example number 4, just like with our problems here in 11.6, when we had irregular shapes, we broke them up into basic shapes that we knew. Same idea here. This is an irregular shape, but this is a basic shape for us. It is a volume of or it is a pyramid, and this is a prism underneath it. So to find the volume of this irregular shape, let's find the volume of this prism, which is a cube, and then add it to the volume of the pyramid, on top. And you know how to do that with these, the volume of a cube, a prism, and also the volume of a pyramid. And in this example here, again, since this stuff is so easy, what they're doing is let's use this skill in a real world problem. And they have us a funnel, they give us a funnel here, and we want to figure out the coarseness of a particular type of sand, meaning how large are the granulars of the sand, and you can determine that, or a factor, a measurement that helps us to determine the coarseness of it is how quickly does it flow through a particular funnel. As you know, if they were larger grains of sand, it would be slower to flow out through a funnel. If you had smaller grains of sand, it would be faster. And of course, if you pour water, some liquid that has a low viscosity, that would flow in through your funnel very quickly. So let's first figure out the volume of this cone, this volume, and I guess they're assuming that, well, actually there is some, inaccuracy here, because of course the cone would come all the way down to a apex, whereas our funnel does not. It comes down to a cylinder. So there is some difference here, some tolerance, some inaccuracy in our measurements, but we're just kind of doing a ballpark figure. So here's our volume of a cone. Will be 1/3 base, the area of the base, times the height, and the shape of our base is circle. Here's our base up on top here, and so the area of a circle is pi r squared, and so that's where that formula comes from. We plug in what we know, and so the volume of this, approximately, the volume of this cone or this funnel is 101 milliliters. Milliliters are equal to centimeters cubed. That's a great system, isn't it? Metric system is nice because you can go straight from centimeters cubed centimeters to milliliters. It's a one-to-one conversion. And to find out the speed of this particular sand going through, well, actually they give us the speed, don't they? Well, no, they give us the time of 2.8 seconds. So to find the speed of this particular sand going through this funnel, you would take the volume of the funnel, which is the volume of the sand when you fill the funnel up completely, and then divide that by the time that the sand takes to pour out. And so if you divide those numbers, you get 36.07, and it's approximately milliliters per second. And so the inference here is that you put a different sand in with a different coarseness and measure the amount of time that it takes for that sand to flow through your funnel. And the assumption is that it would take a longer time, it would take more than 2.8 seconds for a coarser sand, a sand with larger granulars, to flow through, and it would take a shorter time for sand with a lighter, smaller coarseness, or smaller coarseness. Okay, so you ready now for your two problems here? And I did not include problem 6 from the book, but just problems 4 and 5, and you should be able to do that with no problem. Hope you do well. Please put the energy into it on your own. Don't just copy down what I'm doing, and I look forward to seeing you in class.